Thank you. So for this discussion tonight, I wanted to talk about the importance of systematic imaging on long-duration rover missions. And I want to thank my co-authors, Eileen Yingst and Michelle Minitti and Barbara Cohen for contributing to this. Next slide, please. I know that's sort of difficult to see on here, but the point of this figure is to talk about how this rover has the opportunity to explore a lot of different places in the south pole of the moon. And what that means is we really need to think about, for a long duration planetary rover like this, that a consistent and systematic imaging plan is imperative for assessing surface features over the long distance that this rover will be able to work in throughout its mission. Next slide. So high resolutions images that are collected at multiple scales. And so we are talking about not like context images like these beautiful ones that you see from Apollo and Chang'e, looking at the landscapes that surround them, but also thinking about smaller scales. We want to be able to collect these systematic images to really be able to compare different parts of the mission to each other during this time. And so these are really beautiful landscapes, but and they're gorgeous to look at. But as you go to the next slide, we also need to start to think about images that capture material that is on a much smaller scale. And that really requires science-rated cameras versus off-the-shelf ruggedized cameras that have a resolution specifically designed to discriminate key geologic features. And so I really like this figure from Keen et al. At LPSC this year, which really shows how diversified the regolith is, that you can have, because the regolith is broken down and that material is transported across SPA, that as you travel across SPA, you're really going to start to just get different puzzle pieces from every single mission. And so to really start to understand those puzzle pieces in the regolith that you can see across a long duration mission, you need to have a high fidelity imager that can actually discern against, like on Mars, we talk about the importance of sand versus silt sized grains on Mars, because that was something that was absolutely necessary to talk about the history of water. And so when we're talking about the moon and we're thinking about the average size of a regolith, it's about 72, 74 microns. We really need to have an imager that can accurately collect images at that size. And so the other important part of a science-rated camera is that we can actually calibrate those camera and those images beforehand and throughout the mission with the inclusion of a calibration target. And then we can have that data and the calibration target available to the science community and to the public for future science investigations if we want to collect this data. And so the next couple, we've used this method on Mars before. And so the next couple of slides actually show some of these examples. So next slide, please. And so what we're really saying is you need to collect images, not just when you see something really exciting, but it's really crucial to collect images that over long durations reduce bias in observations. And so the Mars rovers have been doing this for a long time. And so this is one of the examples. I have a couple other coming up, which is every time the rover finishes post drive, and I'm talking about MSL with Mastcam, we take a fixed pointing as a way to document the terrain at every stop. And so this is one of those mosaics. And as you can see, you're able to pull out some very interesting rock textures and shapes that you might not have chosen to see, and they're at the smaller scale, but because we collected just an image mosaic at that location, we are able to collect and start to build our understanding of the surface. And on to the next slide is another version of this. And so we have been using the MARTI camera, which is the Mars Descent Imager, which did an amazing job as the rover descended to the surface, but actually now has become a really good non-biased imager. And so at the end of every drive, this camera is located below the body of the rover and actually collects an image at the end of each drive. But we've realized that it could be really useful as you go across different transitions of units, that you can collect what we call a sidewalk. So we can collect the material that's going underneath the rover wheels and looking for those, contact points and seeing exactly how that material transitions at a much higher resolution than if we did looking at it with the mass cam or the other or the engineering cameras on the rover. And so this is a sidewalk mosaic that was obtained as we were climbing up onto this plateau. And so each of these images is actually about 80 centimeters across. And so it gives us a really detailed ability to see changes as you go across these contacts. Next slide, please. And so we really need these imagers that can collect data at the resolution needed for science. And so, as I've said before, here are some other examples. Another way that we do this, you see one of those singular MARTI images on the right, but we also take a class survey after every drive or every amount of distance that is predetermined by the team. And so this is just to look at the changes. And so you see on the left side a bunch of different examples of different class that we've been able to see. And I can imagine that as the pressurized rover is roving across the South Pole of the moon, you might actually see different changes in material, different changes in grains, maybe different changes in block abundances that could be imaged and characterized by systematic imaging and give you a very non-biased approach into making those observations. Next slide. And so these imaging plans can be designed for science investigations, instrument workspaces, we can have panoramic images, pre or post-drive scenarios, and surface, which means that these imaging plans can be utilized during both the crew and uncrewed portions of the mission. And so an example of very similar to what we do on Mars is every time a traverse ends, we take a panoramic mosaic. There were sometimes we take the MARTI image looking down. We have taken landscape images before in the past, but we have built up a very simple cadence. And this cadence is really important because if you do the cadence every single time, not only do you collect a systematic set of images, but you also do reduce, it's not very complex. Once you actually build a sequence of images, you can have that sent to the rover and have it happen every single time. And so I imagine this working really well through the traversing and even the robotic exploration stage. And then especially in the South Pole during the recharging phase, maybe you can look for changes if there are volatiles in the area and take systematic images to look for those changes during the recharging. Next slide, please. Another thing to consider when thinking about systematic imaging is you can do stereophotogrammetry. And so this would actually enable us to model the lunar surface terrain. And so here's another example from the Mars rover with the MOLLE camera. We collect QRMs or quantitative relief maps by taking an overlapping cross pattern of 5 images with the camera on the end of the robotic arm. So this is a very high fidelity version of this, but it allows us to actually recreate these terrains on a very small scale. We can see small scale textural changes. We can see grain shape and size changes. And even if you don't have a high resolution camera on the end of the arm, you could collect still stereo pairs to be able to model that reconstruction. So thinking about having 2 science quality imagers with potentially overlapping fields of view, or even if you just have one imager, having the ability to translate or move the rover to collect overlapping images to collect those stereo pairs. Next slide, please. And so in the context of the pressurized rover, we can use multiple mounting positions, potentially at the front or in the back of the rover, or next slide, please. Or potentially even thinking about maybe on the back of the rover, which isn't a designated position right now, but could give you the opportunity to image the the rover tracks and inform regolith property investigations. Next slide, which is my last slide, I believe. Oh, and you could see Yingst et al. For imagers at the end of the arm has a really great presentation on that. And last slide then. So my conclusion, systematic imaging plan would greatly benefit long duration rover missions, and it reduces complexity and allows you to compare images across the source of across the long-term duration missions. And thank you very much.